started. Okay, welcome to Thinking Beyond. Before we get started on tonight's webinar, I, of course, have a few announcements. And the first announcement is that our next two webinars for Thinking Beyond, we have Jim Benford in March, and his talk is titled Sailing to the Stars, New Technology Could Get Us There. And April's speaker is Howard Weissman, and his talk is Turing-Wigner-Bell, What Thought Experiments with Quantum Computers Tell Us About Thoughts. And these will be, as the usually scheduled, the last Monday of the month at the same time, which is 6 p.m. Mountain Standard. And then for those who are in town, we have, as you can see on your screen, our Beyond Annual Lecture on March 31st, and registration is now open. It's at 7 p.m. in Marston Theater. So you can head over to the Beyond website and register for that. And then for tonight's webinar, as usual, if you have any questions, just submit them using the Q&A button at the bottom of your screen, and we will get to those at the end of the hour. So I don't have anything else, so I'll just go ahead and turn it over to our moderator for this evening, Paul Davies.
Thank you, Jessica, and welcome everybody to another exciting Thinking Beyond. And even if you are out of town, do think about coming to Tempe, coming to Arizona for our Beyond Annual Lecture, because we think it's going to be a very special event. But today, it's my pleasure to introduce our speaker for today, and this will be followed as usual by a little bit of discussion and a good opportunity for our audience to join in the Q&A. So David Blair is a very old friend. We go back a long way, and David's interests are very diverse. So he works at the University of Western Australia, that's in Perth, and most of his career he has been best known for his work in gravitational wave astronomy. And so that's been a dedication, because it's taken decades and decades for this to come to fruition. But as part of the LIGO project, he was able to celebrate in 2015 the first successful detection of gravitational waves. And this is a field which is now part of a new window on the universe, a new branch of astronomy. But today he's here not to talk so much about that, but about his interest in extraterrestrial life and intelligence and SETI and interstellar communication and possible interstellar travel. And he has a new book, which he's just written. David, I've forgotten the title of the book. Do remind me.
It's Where is Everybody?
Where is Everybody? So if you enjoy this presentation, then watch out for that book. It should be coming in the next few months. So without further ado, I'm going to hand over to David, and he's going to address the challenge that interstellar travel is bunk. Oh, I should mention, for those, David and I are of a similar age, but many of our audience are younger, and they may not know that this is an allusion to the Astronomer Royal. His name was Spencer Jones, I think, in the 1950s, Britain's Astronomer Royal, who famously said, space travel is bunk, I think a couple of weeks before the first Sputnik was launched. So that's the background to the title. David, over to you.
Thank you. So I'm going to share my screen. I've got about 19 slides to just guide me. And I'm trying to share and press the play from start button, and you should be able to see my first slide. Paul or Jessica, could you just tell me if you can see that okay? And you can hear me all right?
Good. Can see,
Yeah.
can hear.
So there is the cover of my book, Where is Everybody, which is a quote from Enrico Fermi. in the 1990s, I led the first SETI searches in Australia using Parkes radio telescope and also the Lowell optical telescope, which I think originated at Lowell Observatory, not far from you. The but I also lead a project, and this is what keeps me busy most of the time, called Einstein First, where we believe that by the age of 15, every child should have a basic understanding of physical reality. And our program is training teachers, large numbers of teachers, to teach modern science concepts using activities with for very young children. It's been brilliantly successful. But let's move straight on to Enrico Fermi and the bomb maker's lunch. And probably a lot of people have heard about it, where he asked that question, where is everybody? And he is said to have commented somewhat later, it might be that interstellar flight is impossible, or not worth the effort, or technological civilization doesn't last long enough. So the first and the third points are the things that I'm going to be particularly talking about. And but the other inspiration for my talk and my work has been Ron Bracewell, the great pioneer of radio astronomy, who built the Bracewell radio telescope at Stanford during the Apollo era to monitor the sun. He's the pioneer of synthesis radio astronomy and of medical imaging. So every time you have an MRI scan, you can thank Ron Bracewell for the software that lets you see the insides of your body. But in 1960, he wrote a paper which not many people seem very aware of, but it was published in Nature, called Communications from Superior Galactic Communities. And in that paper, and I should point out this is a year before the Drake equation arose, and yet it is basically inside Bracewell's paper. And he made an estimate in that paper of the lifetime or the distance of civilizations as a function of their lifetime. He realized that fundamental connection between distance and lifetime. And the black line that you can see in the bottom right is the curve that he predicted. And blue dots on there are latest data from the Kepler mission and other missions discovering exoplanets. And it fits absolutely perfectly. And remembering that Bracewell, there were two things important about this. First of all, no exoplanets had been discovered at that time. And secondly, the internet had not been invented. And and yet his prediction was that there exists a galactic club of civilizations, a galactic internet, streaming signals from civilization to civilization, and it probably has existed for at least 5 billion years. That is his prediction. And I want to now to step through the logic that points to that being a very likely occurrence, and more than that, some optimism. But behind that, it has to be also the title of the talk, that interstellar travel is bunk. So let's just run through a few slides to look at the basic points here, starting from the idea of life, that life involves replication, and replication means doubling. Doubling means exponential growth. And if things are growing exponentially, you need more resources, you need more space, you need to explore. So exploration has to be intrinsic in any form of life, anything where doubling is taking place. So the will to explore, I believe, is a universal property of life. It happens at the level of molds in your refrigerator or in your fruit box, and it happens at the level of civilizations in the galaxy. And throughout the history of life on Earth that we know, what we see is that life is an inventor. Life invents concepts and it invents technologies. Examples of the concept, one of the fundamental concepts is symbiosis. For example, multicellular organisms that work together to achieve achieve more expansion, more survivability, or whatever it may be. But life also invents soft technologies like eyes and a myriad different technologies that are parts of our bodies. We don't normally call them technologies, but I'm going to argue that those technologies are really not so different from another set of technologies, which are hard technologies, such as body armor or stone tools or computers. And these examples tell us why it's likely that the galactic internet exists. So I want to take you through the sequence that takes us to that point. So this idea of symbiosis, it's a universal tool for growth. Ever since the first two cells joined together, and survival was better with two cells joined together than two cells separated. Symbiosis gives mutual benefits. Farming is a symbiosis. Pollination is a symbiosis. There's symbiosis everywhere. But there's also a sort of symbiosis, but you might argue whether it is or not, which is between technologies and life. But the outcome is that the technologies evolve with life. And examples are stone tools and farming and electricity and maybe the culmination of all of that, photon technology. And I'll say a little bit more what I mean by photon technologies in a moment. But the crucial thing about these technologies is that they outlive species. Body armor has survived several mass extinctions. Seashells and things like that have been around for 600 million years. Stone tools evolved and survived 10 Homo species, multiple ice ages, and 9 extinctions. We're the lucky one that's still around. And the inventor of stone tools had a third of our brain size. So we can't say that tools are something special about ourselves. They are something that life invented, and we are just the inheritors of that technology. And farming has evolved across multiple civilizations. Farming doesn't stop when one civilization collapses and another one takes over. The technology survives. Electricity and magnetism, which were discovered 2,500 years ago, evolved in a relatively natural way into photon technologies, radio and lasers, and understanding of the whole photon spectrum. So the point is that civilizations pass, but technologies survive. And we shouldn't ask how long does a civilization last out in the galaxy. What we want to ask is what's the lifetime of the technologies that allow communication. We'll see that that becomes a crucial thing. And one of the most important discoveries of life's discoveries is the laws of physics, which were discovered in the first 20 years of the 20th century. the the idea of universality and indistinguishability. We ought to look at that as a single finite stepping capability. We talk about general relativity and quantum mechanics and all sorts of details, and it's easy for us to break it down into details. But behind it is a single finite step in our capability, which was this discovery of the laws of physics. It's like the discovery of stone tools, or the discovery of fire more than 1 million years ago, or the discovery of farming 10,000 years ago. Life is suddenly able to determine what's possible and what's impossible. This set of discoveries from the early 20th century didn't give us godlike powers, even though it seemed like it when nuclear weapons were invented and things like that. Um, uh, but it gave us knowledge, and it gave us restrictions and limits like the speed of light. It's got no loopholes. And even though science fiction writers, especially, would love to have to find those loopholes and use those loopholes to invent wonderful stories. But um, but the point is that once a new technology is introduced, it tends to grow exponentially. And during the time that the technology grows exponentially, it's very easy for people to look at that exponential growth and say, this is going to go on forever. This is the danger zone when you get into all sorts of fantasy predictions, like the prediction that we can travel to the stars and colonize the Milky Way galaxy and all sorts of things of that sort. Those things are essential for science fiction stories, but they really are fictions because they are impossible extrapolations. The real curve is the red curve, not the blue curve. Uh, so universality of physical laws also implies the universality of life. And the recent discoveries tell us that there are around 10 to the 11 Earth-like planets in the Milky Way. It's an extraordinary number. They've got the same physics, the same atoms, the same limits to technology. They're bound by the laws of physics just like we are. Um, and there's like on Earth, we see convergent evolution, like the 40 times that eyes have been invented independently by evolution. So presumably, it's at least a good guess that there is a convergence to somewhat similar solutions. I'm not suggesting that there are people running around looking like human beings on other planets. I really can't speculate about that. But what we can say is that there's a universal demand for exploration because exploration is intrinsic to life, as I already emphasized. So I like to think that the aliens are our siblings. Our parents are the laws of physics. Life on Earth is our best estimate of the mean. It's our only sample, and we have to work with this single sample to make our best estimate of what is there. But the variance is unknowable because that's a law of statistics when you have a single sample. So then they want to explore. So how do they explore? Well, there's only two ways to explore, and one is physically by spacecraft, and the second is by communication. And and the title of this talk is to put to bed this question of interstellar spacecraft exploration, that it's an impossible fantasy. So there are three ways that I want to mention that have been discussed, and proposed as realistic ways of doing things. One is the most recent is the Breakthrough Starshot project, the idea that you can send spacecraft using radiation pressure at 20% of the speed of light. But that doesn't work because space becomes radioactive. And I'll say more about that in a moment. I'll show you just two or three pictures to set the scene, and then I'll come back to that question. Slow travel is what we know how to do now. The Voyager spacecraft are examples of our slow travel, and we've shown that a spacecraft can leave the solar system and is and can survive for 50 years. But that does not that is really quite insignificant. And the reality is that enormous gamma ray bursts are inevitable if you take the slow travel route. Science fiction stories love the 1G travel idea, and there's very popular science fiction stories that use that idea, where a rocket accelerates half the journey and then decelerates for half the journey at 1G, so you feel nice and comfortable. It's all great, except unfortunately, it violates the laws of physics, and I can tell you why. So behind it all is the idea that it is completely absurd to move bulk matter when information suffices. So just the background on this is the Breakthrough Starshot project. There's Milner and Hawking in 2016, and Dyson, and they pledged $100 million for this project, and they were going to send a spacecraft at 20% of light speed from here to Alpha Centauri in 20 years. But this had been proposed earlier by Robert Forward in 1985. Exactly the same concept, 20% of light speed, same time. And the only thing is they didn't have Forward didn't have $100 million to put to it. And the other difference is one was going to use microwave and the other was going to use optical photons. And on their website, they even put up this picture. The whole concept violates laws of physics, including this picture. And I hope some of you can see how this picture is a total violation of the whole concept behind it. But let's just now, and this is the one slide I have with a whole lot of detail, just because I wanted to tell you a few numbers. The main thing is that interstellar space is filled with a thin gas. That thin gas is about 1 million atoms per cubic meter. And at 20% of light speed, a high school calculation can show you that you are hitting these atoms at with an energy, or the atoms, by relativity, the atoms are striking the spacecraft at 100 MeV, a significantly high level of radioactive energy. There are 10 to the 18 radiation counts per light year in the tiny spacecraft that Breakthrough Starshot had proposed. There's 1 billion radiation counts per second. It's 10 to the 8th times the radiation limit for electronics. The electronics is basically just destroyed. And 1 million plasma balls of dust will collide with this thing every light year. So it's like taking a USB chip, which is the sort of size that was proposed for this thing, and drilling 1 million holes in it and wondering if it would still work. Very simple physics completely rules out that project. The alternative is we use rockets like we have today, and then the journeys to the stars are 1 million years long. If you're going to go, say, 100 light years, you're traveling at 10 to the -4 of the light speed. So you just multiply the distance of the star in light years by 10,000, and that's how many years it will take you to get there. But we've got to understand what 10 to the 4th increase in time involves. This means that unobservably rare gamma ray bursts become inevitable. They're unobservable because in 50 years you don't expect ever to see one. You only expect to see them on the rate of perhaps one every 100,000 years. But those will be powerful enough to destroy the spacecraft. The This third possibility, I think I won't say any more about, um, except to say that it violates E equals mc squared by a factor of 100. So interstellar travel is eliminated from our thinking. The only thing left for us is communication. That's the way to explore. And symbiosis saves the day because exploration by communication involves symbiosis. It involves the cooperation of two civilizations or two life forms in two different places in the universe. The beauty about communication with photons is it's got minimum energy, minimum latency. In other words, the time for a reply is almost reasonable. It's still really annoyingly large, like to Alpha Centauri, the latency is 40 years, 20 years for this, sorry, 80 years because it's 4 light years, 4 years to get there, 4 years to come back. Bracewell shows why it's reasonable to think that this communication technology is likely to have evolved at least 5 billion years ago, perhaps 8 billion years ago, and the technology involves directed beacons and beam data streams. So beacons to alert people, that's how you initiate the symbiosis, and the data streams is now providing that satisfaction of exploration, of providing information across the galaxy. So this could connect the entire galaxy. It needs only reasonable advanced astronomy. There's really nothing much we have to do right now. The two-way latency means that the first beacon could arrive this year, and it might not arrive until say 2400. It will be perhaps hundreds of years in the future. 2400 is a rather arbitrary number, but I wanted to give you a scale. Also, with technology we already have, naked eye detectable beacons are possible, and I think that's very important too. So the Earth's membership application for this galactic internet has already been sent, and it looks a bit like a big bubble expanding out 1 light year every year. And that is the radio emission from the Earth in the 1960s. So that is spreading out, and it has now reached 3,000 stars. Here's a picture of what the Milky Way galaxy would look like, and I put a little circle there for where we might be in the Milky Way, but that circle is not the bubble. That circle is 100 times bigger than the bubble actually is. So we this bubble of radio emission has only reached a tiniest fraction of the Milky Way galaxy, but it does allow planet Earth to be distinguished, or the sun to be distinguished from other planets that do not emit radio. That's the signature of life. So just to finish, I want to show you a little just animation on this slide. This is Bracewell's picture, Bracewell's graph again from 1960, but then to show you where the numbers fit and how it looks. If the technology lifetime was 1 billion years, which I don't think is very realistic, but I really don't know how to even make estimates about this, then the nearest civilization would be about 10 light years away. We should have had a reply already. If it's 1 million years, which is 3 times as long as one third of how long stone tool technology has lasted, but about the lifetime of most species, then it's about 100 years distance to the nearest civilization, and then it's about 200 years before we get a reply. At 10,000 years, it's 1,000 light years away. And at 100 years lifetime, which many people would say we invented radio 100 years ago, and we're just on the point of destroying ourselves by nuclear wars or climate change or overpopulation. So if you take that doom and gloom picture, then it's 10,000 light years away. And what does all this mean in the big picture? It means that all that bottom rectangle is impossible. It's impossible because there's no point in sending a beacon because by the time of the reply, you won't exist. But if you're in the top left part of this graph, it is possible. And that way, this galactic internet can exist. So the galactic internet can exist if civilizations can last for 10,000 years, as long as agriculture has lasted on Earth. Um, and so we could really expect something. So my finish is to say that there is an optimistic prognosis based on technology lifetime and this idea of symbiosis, that they cooperate and helping us to join. We're like the first two cells that join together, except that first cell is actually already part of a huge network. We sent our signature in the 1960s. We should anticipate a beacon and consider how to decode it and what we might learn. And people have already thought about many of those things. The Rubin telescope is a wonderful telescope that is scanning the sky every 3 days, just come into operation. But also radio telescopes and naked eyes can detect the first beacon from now to 2400. And if we get a beacon, it instantly tells us that life doesn't destroy itself in some sort of exponential catastrophe, which many people have suggested is likely to happen. So that's the story. And I should say that you can not only can you get this "Where Is Everybody" book to read a much more detailed discussion of it, but also I have a fictional version of this, which is called Starstream, which is published on Amazon, and you can find that and get it for very little money. Thanks very much. So there's my thesis.
That's wonderful, David. Thank you. And a lot of ideas that you held out there. I've got a few questions of my own, but for our audience, please do use the Q&A channel to submit your questions, which we'll come to shortly. But let me just ask my co-hosts, Sara and Maulik, whether they have any comments or questions that they'd like to put to you.
Thanks.
Yeah.
Go ahead, Maulik.
Hi, that was a fantastic talk. Pessimistic, but based on physics. So, well, so you had this log plot basically that showed the distance to the nearest civilization based on technology. So there's an order one numerical coefficient in front that's not determinable from that, right? So it depends sort of on the density of life in the universe. Is that what goes into that?
Oh yeah, yeah. It's something that you can derive from the Drake equation if you make some optimistic assumptions about the various coefficients that Drake proposed. But what I'm arguing here is that technology is a natural and inevitable outcome of life And so everywhere that life exists, technology emerges. So in a sense, I'm putting all the coefficients in the Drake equation to one, the probability being one that these things happen. Of course, 10 to the 11, there's one thing that's in our favor. If you change the number of Earth-like planets from 10 to the 11 to 10 to the 10th and say only 1 in 10 of those planets is actually suitable when you look at the detail, you only change the distance by a factor of two, or because it scales as volume. So two cubed is nearly an order of magnitude. So it's rather a forgiving situation in terms of distance.
But so that was sort of the best possible coefficient that you could have picked by putting them all equal to all the other quantities to one, effectively.
But I really have yeah, effectively disputing the idea that these. So first of all, I'm saying that when conditions are suitable, life automatically evolves. Life is not an accidental outcome. It is an inevitable outcome of the laws of physics. So where the conditions are suitable, life emerges. So that factor is one. Then I'm arguing that technology is absolutely natural part of evolution. And so where life evolves on some time scale, it will evolve into technology. Now that could be, maybe very strongly disputed by some people, um, but but I think the evidence on Earth, which is our only data point, is really important. Another thing that's really, really important is this single sample problem, the fact that we only have planet Earth to look at. And so it's very interesting to actually look at single sample problems particularly in astronomy. For example, in 2015, when we discovered the first gravitational wave, we had switched the detectors on 2 weeks earlier. And within 2 weeks, we detect a binary black hole coalescence. Suddenly, 2 weeks later, there is this event. And within a day, innumerable physicists had said, what is the rate of these things? What is the total population of these black hole binaries out there? Based on the fact that in 2 weeks of observation, we just saw one. Well, the best estimate is that they're happening of order once every 2 weeks. This mathematically, uh, it's the estimates you can make are usually right within an order of magnitude. And there are innumerable examples in astronomy where a single sample has given an answer which is extremely plausible and proven later to be roughly right, only to within about order of magnitude. So I would say that based on our observations here, then within an order of magnitude, I can say the same thing is going to be happening elsewhere in the Milky Way galaxy.
Yeah.
Paul, you're muted.
Thank you. Yeah, so Sarah, I wondered if you wanted to chip in on whether we should move to some of the audience questions.
I have to run and I'd love to ask a question before I run because it was so engaging. I'm sorry I have to leave early. I just have to pick up my kids. But there's a lot of things I want to kind of poke at. But the last thing you said is actually kind of interesting to me, that this idea that like things that happen for life on Earth are average. And I think some of these statistical arguments work for physics because the kind of space of possibilities is fairly low for most physical phenomena in the universe. But I think when you get to life, because of the richness of the diversity and the combinatorial space, that the nature of probability is a little bit different. And you talked about this a bit at the beginning of your talk when you mentioned about how living things discover the space of possibilities. And I think when you make this sort of leap to intelligence and you actually understand the rules of the game, there's something fundamentally different about the nature of these systems that we're talking about and looking for. And I guess the challenge I have, I really like a lot of your arguments. They're very rich and very convincing, but they're still very anthropocentrically loaded by life on Earth. And I'm just wondering if I was just trying to like look at the statistics and like the data presented to me without having any prior about life on Earth, is there anything that you could do with the kind of arguments you have, or do you have to kind of condition it on events from Earth always in these kind of arguments? Um,
Yeah. So
I mean, it's a
it's
hard question. I don't know how to answer it myself. This is why
no.
I'm asking. Yeah.
So at the people have speculated about alternative bases for DNA and all sorts of different uh, forms that life could be manifest in. And but what we seem to see, and what a huge number of biochemists and people of that sort seem to believe, is that there is one optimal solution for life. Now, I don't know if that's true or not, and how we can find that out is rather difficult. But I think Paul in his books have explored a lot of these questions as well. But somehow it does seem as if the whole system is fine-tuned with one optimal solution. And and my argument about convergent evolution, also perhaps has certain weaknesses because, I said eyes have evolved, very much the same sort of structures 40 times, but they are all built from the same DNA. And so
Yeah.
behind it is the same genetic code. And so there is that commonality. But still, if you follow that argument and you say the genetic code dictates the sort of solutions, then I think it's also reasonable to say that laws of physics dictate the genetic code. And and so by tracing back to the laws of physics, you can argue that there is not such a spectrum of possibilities. So my argument would be that we wouldn't be we would be surprised in the same way that James Cook was surprised or Darwin when they discovered marsupials hopping around in Australia. Uh, um, Nothing, it hadn't been anticipated, hadn't been expected, and there is this other form of mammal. And so there would be all those sorts of surprises when we explored life on another planet. But but my suspicion, but it's only a suspicion, is that you might find exactly the same DNA code because we've read about the amino acids and things that have been discovered in asteroid, the latest asteroid return mission and things of that sort, which seems to tell us that the building blocks, at least, I, were identical, and we are built out of those. So you could expect those elsewhere as well.
Yeah, I have a much longer conversation and debate about this topic, but we'll save that for another day. And I'm so looking forward to when we have that opportunity. I'll let you guys get to other questions, but that was great. Thank you so much.
I do bring in the audience questions, but I just want to, in connection with your last answer, raise the point that Charlie Lineweaver, in his so-called Planet of the Apes fallacy, likes to push. So convergent evolution has given us eyes many times, wings many times, and so on. But if you say instead, look at the elephant's trunk, that seems to be a sort of one-off phenomenon. And then the question is, with intelligence, is it, eye-like or wing-like, or is it more trunk-like? In other words, if something wiped out all multicellular life on Earth and you came back in another billion years, would you expect to find intelligent beings here on Earth? Or was the evolution of intelligence just a freak like the elephant's trunk?
Yeah. The one thing that tells me that it is somewhat deterministic is the log plot of peak encephalization versus versus time. That Russell, I think, was the first person to publish in the 1990s or so. Dale Russell from Canada. And I have a version of that in the Where Is Everybody book. But basically, there is an exponential growth in peak encephalization, only roughly. It's because it's affected strongly by things like mass extinction events. But that occurs over something like 7 decades of encephalization. The so there seems to be something deterministic about the evolution of intelligence, and as I emphasized in my talk, these hard technologies like shells and stone tools and computers seem to follow similar laws. So, but then you could argue, well, why haven't the dolphins invented technologies and things of that sort, there I have to say I really don't know. And this could say that if those planets are water planets, then they will never be part of the galactic internet. And what fraction of the Earth-like planets are water planets? We don't know. The numbers would change, but I still think that given the sample of 10 to the 11 Earth-like planets, we only have to have a tiny fraction of them that match this planet, and we would expect then perhaps for technology to emerge there. And the
So
other
I
thing
think
so
I think
important is there's so much time. We have 5 billion years or 8 billion years when all these things could have happened.
so. We must deal with a few things now. One or two of these are sort of basic engineering type questions, could probably have short answers. So taking them just in the order I received them, Barbara Temple would say, she says, well, why did you take your radio bubble starting in the 1960s? Surely you should go back to the 1920s, regional radio technology, which I think Carl Sagan did in his book.
Yeah, and actually, that is very easy if you take the modern quantum approach um, to looking at radio and light and things of that sort. I don't know if you're aware, but people are just at the point of improving radio receivers to the point that they can count individual photons. Um, the and Optical telescopes are already at that point that you count the photons coming in. So the question is then, how many photons do you need to receive to be able to be able to tell that that there was a technology emitting this unexpected radiation from the solar system if you're at a distance of 100 light years away. And then you can say, now what size telescope do I need? Because I need more than one photon to be able to make that distinction. I need to have a reasonable sample of photons. I've got to do that in a reasonable amount of time. So how big does my radio telescope have to be? As soon as you do that, 1920s radio emission is totally out of the question. It is not detectable except with outrageous things. And when I say outrageous, I mean, for example, a planetary sized radio telescope. It's easy for us to say, oh, wouldn't it be wonderful to build a planetary sized radio telescope, just like the Dyson sphere idea that Dyson very, very quickly pointed out was dynamically impossible to create around a star. Um, the the strength of materials is one of the things that comes out of physics, out of the physics that we know and understand about interactions between atoms and things of that sort. So, uh, so a planetary-sized radio telescope in space is likely to be dynamically unstable because of gravity gradient forces that act. Now, perhaps you could stretch to a certain, you move it further away from the sun, further away from other planets and things like that, so that gravity forces don't overcome the atomic forces that determine the shape of objects. But ultimately, energy and strength of materials sets limits of what you can do. And that means that these weak radio signals will not be detectable. Also, these radio signals have got to outshine the sun in some way. There are two ways of finding out if you're 100 light years from the Earth, how can you determine whether life exists? You can, if you point most telescopes at the sun, you won't be able to separate the Earth from it unless you build an absolutely enormous telescope. And if you do that, you might be able to start to try to see the photons coming from the sun behind the cosmic microwave background and other galactic radio signals. But when you put in the numbers, all of these things become impossible. So you really need something like a gigawatt of emission, and we have a gigawatt of emission coming from planet Earth now. Interestingly, a lot of it is coming from Wi-Fi and our own phones, which emit watts, not all the time, but watts of radiation. All the cell phone towers are emitting gigawatts of power into space. So of order, a gigawatt of radio emission has been coming out of planet Earth for round about 70 years. But before that, it was too weak, too narrow. There were radars which were narrow beams. They weren't really isotropic. So that's why
Jim,
I think 1960 is roughly the date, around about the time that Cocconi and Morrison made estimates about it.
Jim Benford, who'll be speaking next month, points out that there's a lot of sort of TV and phone signals, but they're not coherent. I mean, sort of jumble of stuff. And even though cumulatively there might be quite a bit of energy, you know, if you're detecting this cacophony, you may not interpret it as a signal rather than
Yeah.
just some sort of noise coming from planet Earth.
And that's a good. That's an interesting point, which I addressed in my book. So it was actually the discovery of how to turn your radio communication into broadband communication instead of narrowband communication. The early TVs were great from the interstellar point of view because because a large amount of the power was in the carrier frequency, but they've abandoned carrier frequencies thanks to Hedy Lamarr and people who invented spread spectrum, 70, 80, whatever it is, years ago. But synthesis radio astronomy comes in here. The synthesis radio astronomy that allowed us to observe the black hole in the middle of the Milky Way galaxy, the Event Horizon Telescope, is also sufficient to allow you to pinpoint planet Earth and see the excess emission without it being contaminated from the sun. So, so radio astronomy, as good as we have on Earth, can still distinguish planetary emissions, even when it becomes broadband. But I should also say it doesn't really matter. We gave out that narrowband signals in the days of analog TV, and and that signal is on its way out there. So that signal is reached its peak in the 1960s or 70s, um, and and that is is our best beacon. But the mobile phones are giving now a big lot of fuzz that even better radio astronomy could identify. So I think we are still identifiable.
Right, now we have the inevitable question. This comes from Eureka Brass, that about the impossibility of interstellar travel. Didn't people say the same, about terrestrial flight? Where I can't. The particular example quoted is 20,000 kilograms at 11 kilometers, moving at 700 kilometers an hour. And the answer is, well, the Boeing 787 does that. So people have always been skeptical about technology, but my reply, but maybe yours will be as well, is that there's a difference between physical impossibility, violating laws of physics, and a technological apparent impossibility. Technology can overcome many obstacles, but can't change the laws of physics, would be my reply. Would you agree with that?
Yes, yes, I would, but part of the laws of physics are things like the strength of materials. So, so whether what you can do in the way of rockets and things of that sort become limited by the laws of physics, at a very practical level. But also, we have to remember, as I emphasized in my talk, this radiation background in space and the fact that gamma rays are very difficult to shield. You can't put up giant superconducting magnet shields to prevent gamma rays. You can use that to prevent protons, but not the gamma rays. So, one thing is these external threats that affect our technology, and that's why time and people being completely unrealistic about the time. The difference between 50 years that the Voyager spacecraft have survived, even having seen a few glitches coming about from radiation, um, and then the million years, our brains are not good at encompassing orders of magnitude. And it's these orders of magnitude that absolutely threaten us in terms of the time travel. But
May I ask another question?
yeah,
Um, so, yes, you've shown that we're going to have this enormous flux of very high energy particles, but there could be engineering solutions to avoiding being hit by those. For example, if you emitted a slight amount of electromagnetic radiation outwards, then from the frame of the particle, that would be very high energy radiation that would ionize it. And then once it's ionized, it's even a small magnetic field in front would deflect it so that you know, it would create a kind of wake around the spaceship. This is just something you could imagine. I don't know if it works in practice, but
well, I think it doesn't work for gamma rays, which are neutral. Neutral. They're just photons. Uh, well,
but
and
those
they
aren't any more boosted than it's the part I'm talking about, the first one where you're going at where you have a short, very high speed travel. That
yeah,
the danger there is that we're going to run into this gas which is going to bombard us at very high energies.
that's
But
true.
but we could, in principle, ionize it and deflect it out with magnetic fields. Um,
Yeah, and if you then ask about the technology to do that, the goal of Breakthrough Starshot was a 1 gram spacecraft. Um, so then you say, now what? A technology to do these things, to shield against this neutral gas. What do you need? I think there's absolutely no way you can do it with 1 gram. You probably need 1,000 tons or something to do it. And as soon as you go to 1,000 tons boosted at that level, you need planetary scale or even solar scale amounts of energy to do it. It becomes completely so crazily
Sure, but
impossible.
not impossible from a laws of physics standpoint. It's just a very, very formidable engineering challenge. I mean, for example, even supplying the energy doesn't have to, the thing doesn't have to have its own energy any more than planes that are, can be refueled, for example. So you could have a set of stations that transport the fuel up the chain or something.
Yeah, well, but if you're going to be doing that and traveling at 20% of light speed,
There,
So this is a wonderful discussion, which could, of course, go on for a long time, but we're out of time. I think your answer, David, was actually the answer to a question that Andrew Crowder had asked. What's happened to breakthrough Starshot, and why is that impossible? And I think you've answered that. But I will tell all of our audience that, of course, Jim Benford will be speaking on this topic in 1 month. So I hope you'll join us then, and and I hope, David, you will find the opportunity to come to that one too, and we'll continue some of these fascinating questions. And sorry that I didn't get around to all of the audience questions, but I hope everybody's enjoyed the discussion today, and that they will watch out for David's book, and look forward to seeing you all in 1 month. So thanks to all,
thank
and
you.
I'll say
Wonderful
goodbye.
talk.
thank you. Thanks very much. I enjoyed it.